Hi everyone. In this video, we'll continue with activity 3, looking at importing and exporting data from R. So we've already looked at in this activity how we can import data into R using the read.csv function. And we've also looked at how we can use the import wizard in order to import data sets into R as well. So read.csv is great in that it is a function that's readily available in R without loading any additional packages. It's fairly simple in that there's not too many ways to customize it. It's a great tool if you have a small, neatly organized CSV file that you want to import into R. Sometimes you have slightly larger data sets, though, that might be too big for, say, read.csv to handle well. For example, in my first year in graduate school, I had to work with a CSV file that contained genetics data for a study that had over 3 million rows or observations and roughly 80 variables. This took many hours. I remember waiting for 4 or 5 hours for R sitting there trying to read in the single data set, and it would end up crashing nearly every time before it could import the data. So this took a lot of my time. Hopefully you never run into something similar like that. But if you do, we're going to cover some better tools besides read.csv for handling these large CSV files or other large data files. So the readr package is a data set for reading or importing data into R made by the tidyverse developers. It's a package that's a part of the tidyverse. Data.table, just commonly called data table, is a package that was, ironically enough, made by professors who were frustrated at trying to work with large genetics data sets in R. So because working with that type of data took so long, they made their own package that implemented much faster code in R to do these types of things like importing data. And then lastly, the arrow package has a lot of different uses, a lot of different useful functions within it. One of which we're going to look at today is a function for reading what are called Parquet files. Okay. So the read_CSV function from the readr package functions essentially the same as the read.csv function. So we can try to import the data again right from the URL, this time using read_CSV. And we'll display a subset of the data using the same code as below. So opening up our file from last time, starting activity 3, we'll copy the code in which we first used read.csv, paste it down here, and now we'll change it from read.csv to read_CSV. If we run this code, should give similar results. You may now see this type of output here. R gives you a little bit of extra information, RStudio, when you import the data using read_CSV. So here it says that there were 3 character or string columns read in for this data set. It was a CSV file. And there were 11 columns that were read in as double type variables or numeric type variables. And it lists those variables out here. And then here's the table. So this is, again, from the readr package. It tends to be slightly faster than read.csv, but honestly, it's more popular for its functionality, its ability to handle special characters better when those are included in the data set. So look at the help file for read_CSV. There's a lot more options and ways to customize the data set. You can have like a progress bar show up. If it's a particularly large data set, it'll show what percent has already been read in, which is kind of handy. All these types of things that you can't do with read.csv. So it has a bit more options, but can still be used in a very similar way. Sort of like a new and improved read.csv, but it's not crazy faster. It's not a considerable amount faster yet. So I still, like in my case, when I had that extremely large data set, this would not have been an ideal option still, because it's only about, I would say, 50 to 30% faster. You might cut the time in half, but if it takes 10 hours to import a data set, 5 hours is still a pretty long time. Okay. So how can we get even faster? Well, one approach that other people have taken, and this is outside the R community, is to recognize that CSV files themselves are not the most efficient for reading and writing data files. So this newer and increasingly common type of data file to use is called a Parquet file. And here I link to a description if you want to read more about this Apache Parquet type of file. So CSV files, which are depicted in this first top table, typically have well, not typically, this is how they are stored. They have the value for the first variable, and then the value for the second variable, and the value for the third variable, and so on. And then when it gets to the next row of the data set here, then it is the second value of the first variable, second value of the second variable, and so on. And when a computer imports a data set, it starts at the top and reads left to right through each row, and then we'll go and start at the left again on row 2, and then it'll read and go and start on row 3. This can be inefficient in certain ways. So for example, if column 1, which is variable 1, is a numeric type, this might be numeric, whereas variable 2 might be a string or character variable. You might have another character variable, and then maybe the fourth column is a logical type variable, true or false values only. So you could have numeric, string, string, logical, numeric, logical. And as the computer is reading in those values, it would have to alternate between those different data types that it's parsing through, which can be a little bit inefficient and time consuming. For data sets with just a few thousand rows or less, that amount of computation is still so small that we wouldn't notice it. But it's when you have millions of rows or more, that idea of the computer needing to switch between the types very often can slow it down so much that it ends up taking hours. So instead of storing it in this type of format, containing the same information, a column-based storage format, which is what Parquet files contain, have the first variable take up the entire row, first row of the data set. So it's the first value of variable 1, second value of variable 1, third value of variable 1, and so on. This allows for a consistent type of value as the computer is reading it, and it goes through the entire first row. So if you had, like in my case, the 3 million observations, it would read 3 million of one type of a variable, say a logical variable, in a row before it had to switch. Much more efficient when you have a large number of rows in your data set, which is most common. So that's one reason Parquet files can be more efficient for reading and writing data sets. There's other reasons as well that improve upon how much space these types of files take up, which is also sometimes a concern. So Parquet files can be much more efficient in terms of how much storage they require for storing that data file, whereas CSV files can be really big, but still just conveying the same amount of information. So if there's all these benefits to Parquet files, why don't people use Parquet files instead of CSV files all the time? Well, it's because CSV files were around first. They're popular and commonly used. And so it's hard to switch away from something when everybody's using that type of data file type. But some people are enough as switching to like Parquet files, as big data is more and more common these days. So we're going to practice seeing how we can read a Parquet file into R using the arrow package, and specifically the read Parquet function from the arrow package. So unfortunately, you cannot read the Parquet file directly from the URL. So we have to download it and upload it to RStudio Workbench, or if you're working with RStudio on your own laptop, just download the file. So clicking that link should download it automatically. Then in RStudio Workbench, we will upload it. Selecting the Parquet file. All right. And now we're going to import this into R. So we're going to add a new chunk. Oops. And we will we'll create a new data set called possums. And then we'll use read underscore Parquet. And if we see the file over here in the files pane, which you should after uploading it, we can get the file path by checking it. More, copy folder path to clipboard. Which in this case, it's not very long. And then you have to add a slash and then the file name at the end of this path. So one way to get that, rename, and that allows you to copy it if you clicked rename. So we'll just leave it. We'll just leave it as what it was named, and then paste that right over here. Okay, so notice there's no spaces in this file path. And then we can import the data like this. So we end up with the same exact data set as before. That's how we can import Parquet files. So now we'll display a subset of the data using only the first 5 rows and the first 8 columns. So thinking how we did this before, maybe copy this code and see how you can modify it and use it on your own to do this. First 5 rows and 8 columns. You could pause the video and try it on your own if you want. Okay. And now to see how we can do that. So slice head prints the first 5 rows. We want the first 8 columns. Change this. Five rows, first 8 columns. Okay. And then print it using the cable function. So there we go. Oh, oops. I actually want to do it like this. There we go. Okay, now it prints the data set here like this. All right. So that's how we can read a Parquet file. That's helpful if you're given a Parquet file and you're trying to analyze it. It can also be helpful to use if you are in a situation where you're working with a very large data set, again, with maybe millions of rows, and you need to keep repeatedly like exporting it out of R, saving it, re-importing it over and over again as you work with the file across time, because each of those processes could take a long time. If you switch it to a Parquet file at some point, you could save yourself a lot of time in the long run. And we'll quantify exactly the difference in the amount of time it can take here when looking at these different file types and working with them. So an option for reading CSV files that's actually still very fast is from the data table package. So the fread function, again, works just like read.csv, but it's much, much faster. So let's directly read in from the URL, which is nice that fread can handle that as well. Let's directly read in that data set again, now using the fread function from the data table package. We can copy the read.csv code from before, change it to fread, all lowercase, and then we can see how that, see if this works. Okay. Yep, great. So that worked as well. When the data set is this size, 100 observations, 14 variables, again, there's no benefit really to using something besides read.csv or read_csv, but it also doesn't hurt. So this is faster, but both are nearly instant for this small of data. So let's compare when it's actually pretty big data. So technically, this is not what would be defined as truly big data. I would just call this like a larger data set. But using this code, we can generate 50,000 observations of 2 variables and set roughly 10% of those values to being missing values. Okay. So we'll just copy this code verbatim. And paste this into a new chunk in our markdown. Okay. Then we can run this code, which will generate that data and then save this generated big data to external files. So here we used the fwrite function from data table to create a CSV file of this data set. We used the write_Parquet function from the arrow package to create a Parquet version of the data set, which you can see. Let's see. Yeah, they showed up over here. And then lastly, a file type that we didn't look at yet is a .rds file, which is a R-specific file format. And so we saved that using the write_rds function from the read_r package. So all of these, we created these files because we're going to practice or explore how long it takes to read these back in using different approaches. So these are all the same exact data set. They contain the same data, but we'll see how some file types and functions that we use can affect the amount of how quickly those get read back in. We're going to consider 5 different functions to compare: read.csv, read_csv, fread, read_Parquet, and read_rds. So first, we're going to create this table that shows the minimum amount of time the function took to read in the data set, the median amount of time, because it'll try and read it in several times to get a good estimate of how long it takes. And then this memory allocation describes how much RAM, how much memory it took while reading in the data set, which can vary depending on the file type and the function that you use. So let's copy this code verbatim again. We're going to write a new chunk. And I guess maybe we could be adding in some text here in between the chunks to describe what we're doing. So first, I suppose that's good practice to do. Okay. The read underscore CSV function works similarly to the read.csv function and be slightly faster and has more options that can be customized. Okay, and then cat files use column-based storage rather than row-based storage. And then the fread function is one of the fastest methods for reading CSV files into R. Okay. And I say it's one of the fastest because there might be a function I'm not aware of that exists. But in terms of what I have found, looking around quite a bit, fread, in my experience, is the fastest possible way to read a large CSV file into R. Okay, and then in this last chunk, you could say beforehand, now we will generate some artificial data to demonstrate different import speeds. Okay. And then this will produce a table. Okay. And this is optional. You don't have to type all this, but it's good practice to indicate what's going on with your R code in between the chunks. Okay. ggBswarm must be installed. Use type equals bswarm option. Okay, so we can install ggBswarm. So we'll do install.packages. Then we'll hit enter. Okay, and that looks like it installed correctly. That's great. Now we'll try to run this again. All right, so here's our table. So this code, we can see that the read underscore RDS function read in the files the fastest in just 457 microseconds about. Whereas the other ones took milliseconds. Okay. So you won't get the same exact results as the activity shows due to randomness. And also it depends on what machine. So like RStudio Workbench is really fast and will run a little bit faster than this, which was run on my own laptop. We can also create what are called violin plots. So there's data points and then this like cloud showing the distribution that's reflected both ways, showing the distribution of runtimes for each of these functions to import the data set. So to reproduce this plot, we can copy this code exactly. And we'll learn more about this type of code later in the semester, but for now, we're just going to copy it exactly. And if we click run on this, you should see the violin plots showing read underscore RDS. Each data point is representing one time it imported that data set, tried to, and how long it took. We can see that's by far the fastest option. Read.csv is the slowest. And here you can see what I was talking about. Read underscore CSV improves a little bit, but it's not that much faster. So the main benefit of read underscore CSV is its customizability. But Parquet files are really fast. And then fread actually, even despite having the more inefficient file type, it's pretty amazing how fast fread is for reading in data files. Now, why did read RDS win out against everything? Well, since we're using R, and that's a R-specific data type, R is sort of, it has an unfair advantage in this environment here for reading that type of data file in. Just like probably if you're working in SAS, reading in a SAS type file would be very fast. If you're working in Stata, a Stata type data file would be really fast to read into that. So it's a bit of an unfair advantage, but you won't commonly be given a .rds file to work with. Usually you're given a CSV or maybe potentially a Parquet file, but probably a CSV file. So again, your plot is not going to exactly match this because of differences on the machine this was run on, but for the most part, it'll be pretty similar. So we can also compare how long it takes to export data from R, how long it takes to write data sets outside of R. So we're going to consider 5 different functions again that are all analogous companion functions to the read versions. Now it's write.csv, write underscore CSV, write underscore RDS, write underscore Parquet, and fwrite, which is from the data table package. So we will use the same exact code, but tweak it to produce this table and this plot now, showing the write times, export times. So to do that, let's first copy this first chunk. Copy all of this. Table displaying the varying export speeds of different R functions is below. Okay. And now instead of read.csv, we're going to do write.csv. And we also need to add, let's see, big data. So the first argument in write.csv, it's going to be big data. And then the file path like that. Big data, file path like that. Then we need write underscore. We'll get rid of this option. And instead of fread, it'll be fwrite. Instead of read underscore RDS, it's write underscore RDS. Read underscore Parquet, it's write underscore Parquet. So we're just tweaking this code. And then we'll get rid of this as Tibble equals true option. Okay. And maybe we'll call this, instead of read, we'll call it write. And then we'll update it here as well. Okay. And then instead of import times, I guess we should call it export times. We'll replace it in the 2 spots there. Okay. All right. So we have write BM result, export times, and export times. And then we can carefully look at each of these functions. Each function call should have the name of the data set first, big data, and then the file path to where that's going to be written. Name, file path, name, file path. Name, file path. And note how write.csv writes to a .csv file. Same with write underscore CSV. Same with fwrite. Write RDS, though, the file extension is .rds. And for Parquet, it's .parquet. Okay. So we're done tweaking this code now. This should work if we run this. Takes a little bit longer because writing takes longer than reading. Now we can see there is some dramatic differences in terms of how fast these functions were to export data. So the fastest was write underscore RDS. Slowest was, oh, actually write underscore CSV was the slowest. And then we'll copy this code to create the violin plots. We'll tweak that a little bit, but for the most part, we can use it unmodified. So import times will change to export times now. And that's it. Other than that, we can reuse that code exactly the same. And then we can create the violin plots to visualize what functions were the fastest. So fwrite, again, from the data table package. Data table is really good for working with CSV files in R. It's very, very fast. And then write underscore RDS, also quite fast. But it doesn't produce a CSV file. It produces a .rds file, which is okay if you're the one importing it back in. But some people, maybe a collaborator you're working with, actually wants a CSV file to be working with. So the results varied a little bit here because this found that write underscore CSV was a little bit slower than write.csv, or a little bit faster here, I should say, but that we didn't find that result. And that, again, machine to machine differences can vary performance a bit in terms of how fast writing and reading data happened. Okay, so we looked at a few options. Let's maybe knit this whole R Markdown document to look how it's looking so far. Okay, might need to allow pop-ups. Okay. Now we can see the results we have so far. Okay. So we can see, yeah, RDS files were the fastest to read into R, while read.csv, reading CSV files using that function was the slowest. This was for importing. Oh, and we should update that title, I guess. Comparison of write times. We can re-knit. Okay. So for exporting data, we saw that RDS files were the fastest again using write_RDS. But fwrite was still very fast and quite close. And so one thing to keep in mind is that sometimes you have choice. Like if it's a CSV file, we have a few options for how we can do that. But if you really need, say, a Parquet file, we don't have too many options for how that can be done. Or if it's an RDS file, there's not too many options for that. So the particular file type that you need is a consideration when deciding how exactly to export your data. If it's just you yourself and you're an R user, I think using RDS files is great. It's very, very fast. It preserves a lot of extra, like additional information that's sort of embedded in R objects when you have them as data sets in there. So it's generally good to do if it's just you working with that data because you're familiar with R, you know how to work with .rds files now. If you're collaborating with others, typically CSV files are the way to go. And so I would use fwrite typically to export data in a fast way. Or if the data set's pretty small, I would use write_CSV. So note that all these approaches we've looked at so far, we've been using this, what we'd call tabular data with rows and columns. But you can have objects in R that are more complex than that. So you can have three-dimensional arrays. You can have also what are called list objects, which don't have as consistent of a structure. It's not a tabular form like a data frame or data table is in R. So a list, you could have a list that has multiple vectors in it. That are different lengths, different types. So this, for example, is a list of length 3 that contains 3 vectors, each of which is a different type. The first vector is a string or character type vector. The next one is an integer or numeric vector. And the last one is a logical vector. And they're all different lengths. So you can have this type of object that you store in R, which can be helpful for various reasons. And then maybe you want to save that object, my list. You can't save an object like that as a CSV file or a Parquet file. Unfortunately, it's not an option. So the only way you can save that object if you wanted to re-import it and use it in a future session is by saving it as a .rds file. So that's some reasons to decide on different functions when importing and exporting data. In the next video, we'll look at how you can read some slightly different file types into R using different packages as well.